Hi everyone, welcome to Brainy Elements. Today we are going to discuss 2018 A-Level first structured essay. Okay, first structured essay, first question. State whether the following statements are true or false. Reasons are not required. The polarizability of halide ions increases with increasing size. Correct, right? Now, for cations, we consider polarizing power. Likewise, for anions, we consider polarizability. What factors does this polarizing power depends on size and charge, right? Depends on size and charge. When size increases, polarizing power decreases. When charge increases, polarizing power increases. What happens when polarizing power decreases? Covalent nature decreases, and when polarizing power increases, covalent nature increases. Okay. Likewise, if we consider polarizability, size and charge, it also depends on size and charge. When size increases, polarizability increases. When polarizability increases, covalent nature increases. Likewise, when charge increases, also the polarizability increases. When the polarizability increases, what happens to covalent nature? Covalent nature also increases. Now, when we consider the halide ions, F minus, Cl minus, Br minus, I minus, what is happening here? The charges are same. It has the same charge, minus, minus 1, minus 1, minus 1. But what happens to size? Down the group, what happens to size? Size increases, therefore polarizability increases. See the statement, polarizability of halide ions increases with increasing size. Yes, statement A is true. This is true. Now, this is Roman number 1. Now, we'll look at Roman number 2. Roman number 2. The ONO bond angle of NO2 is greater than that of NO2 minus. Now, let me draw the Lewis structure of NO2 and NO2 minus. NO2 minus. Here, nitrogen is the central atom because it has less electronegative. When comparing with oxygen, nitrogen is less electronegative. Oxygen is more electronegative. So, this is the Lewis structure. How many total number of valence electrons are there? 6 plus 6, 12. 12 plus 5, 17. 17. Now there are two electrons in bond pairs. No? You should subtract 2 plus 2, 4 electrons. Therefore, from 17, if you subtract 4, you will get 13, right? What does this 13 means? Now let me divide this 13 by 2. What you will get? You will get 6 pairs of electrons plus 1 electron. 6 pairs of electron, 6 into 2 is 12, plus 1 single electron. Now let me distribute this valence electron to the terminal atom first, then to the central atom. 6 pairs, 1, 2, 3, 4, 5, 6. 6 pairs are distributed. Only 1 electron remains. Now see, in the central atom, the octet completed? No, octet is not completed. 1, 2, 3, 4, 5, only 5 electrons are there. To complete octet, 8 electrons should be there. Therefore, let me make this lone pair as the bond pair. If I make like this, what will happen? Now you see 1, 2, 3, 4, 5, 6, 7. Now also octet is not complete. Now, if you try to get one more lone pair, what will happen? Now, for example, let me take this lone pair as bond pair. After this, what will happen? 1, 2. Now, how many electrons are there? There are 9 electrons are there. Therefore, if the the number of electrons is more than the octet along this nitrogen, then it is not a stable structure. There should be 8 or else less than 8. There cannot be 9. Therefore, let us keep it as like this. Now you see that now we'll see the charge distribution. Now octet is completed. Now we'll see the charge distribution. Here 1, 2, 3, 4, 5, 6. There should be 6 valence electron. It has 6 valence electron. Therefore 0 charge. Here 1, 2, 3, 4. It should have 5 valence electron, but it has only 4 valence electron. Therefore plus charge. There should be a plus charge. Here there should be a minus charge. Now you see. Now when we see the total charge of the molecule, 1 plus and 1 minus, the total charge is 0. That is a neutral molecule. NO2 is a neutral molecule. Now we'll see NO2 minus. NO2 minus. NO2 minus. Now how many valence electron? 6 plus 6, 12. 12 plus 5, 17. Plus another one more electron, that is 18. Therefore, from this 18, I should subtract 4 electrons, right? Here there are 2 electrons, here there are 2 electrons. I should subtract the electrons in the bond pair. So let me subtract 4. So you will get 14. 14 by 2, that is 7. So how many pairs of electron? 7 pairs of electron. 1, 2, 3, 4, 5, 6, 7. Now the octet is complete in the terminal atom. Now you see the central atom. Octet is not completed. Only 6 valence 6 electrons are there. You should take the lone pair as bond pair. If you take like this, what will happen? Now you see. Now the octet is completed. Now there are 8 electrons. Now we'll distribute the charge. Once the octet is completed, give the charges, formal charges. Here no charge, 0. Here 1, 2, 3, 4, 5, 0. Here minus 1. Sorry, minus 1, yeah. So what is the charge of the entire molecule? That is minus 1. So here the charge is minus 1. So I can tell the Lewis structure that I have drawn is correct. Lewis structure that I have drawn is correct. Now we'll see what's going to happen. Now let me draw the shape of this molecule. How the shapes look like. This is how it looks like, right? Here there is only 1 electron. Yeah. They are asking this angle, theta angle, theta 1, theta 2. Here you see there will be repulsion between electrons, There will be repulsion between this electron and the electrons in the bond pair. There will be repulsion between this electron and the electron in the bond pair. These electrons in, these are the electrons look like. Electrons in orbital. They do not involve in bonds. So the repulsion between 2 electrons, now there are lone pair, there is a lone pair. There are 2 electrons are involving in repulsion. 2 electrons are involving in repulsion. Here the electrons will be pushing these 2 electrons down. This lone pair electron will push the electrons down. So what will happen when they push down? Theta reduces, theta 2 and theta 1. Here you see the repulsion is given by only 1 electron. Here 2 electrons are involving in repulsion. Here only 1 electrons are involving in repulsion. So which repulsion will be greater? This repulsion will be greater. When this repulsion is greater, they will be pushing the electrons more towards inside. Therefore theta 2 reduces. Therefore if I put the what will be the theta 2 and theta 1? Theta 1 will be greater. Theta 1 will be greater because there is less repulsion. So in the now the bond angle of NO2 is theta 1 is this, right? NO2 is greater than NO2 minus. I will see the statement. Then ONO bond angle of NO2 is greater than that of NO2 minus. Correct? Roman number 2 is also true. Okay. Now we'll see Roman number 3. Roman number 3. The London dispersion forces among CCl4 molecules are smaller than the London dispersion forces among SO3 molecules. It's false now. Now you see CCl4 and SO3. Obviously, you know the size of CCl4 molecule is very much greater than SO3 molecule. Then SO3 molecule, size of CCl4 molecule is greater now. You know the London dispersion forces. On what factor the London dispersion force depends on? London dispersion force depends only on the size. Depends on the size. When size increases, London dispersion force increases. When size reduces, London dispersion force reduces. CCl4 and SO3, among these two, CCl4 molecule is larger. Therefore, London dispersion forces of CCl4 molecule is larger. In the statement, they have said the London dispersion force SO3 is greater. Oh, it's wrong. This is false. Now we'll see Roman number 4. The shape of HSO4 minus ion is a trigonal bipyramid. Let us see it. HSO4 minus ion, right? You know to draw the Lewis structure now? I'll just draw it. Now we'll see. Now what's the charge here? There is minus there. This is HSO4 minus. HSO4 minus. What they have said, the shape of the HSO4 minus ion is trigonal bipyramid. Now, what is the VSEPR pair here? You know the VSEPR pair is 4 now. What is this VSEPR pair? It is the sum of sigma bond plus if there is lone pair. The sum of sigma bond pair plus lone pair. Here, there is no lone pair. So, what is the number of sigma bond? 1, 2, 3, 4. What is these two? These two are pi bonds. Pi bonds are not included in VSEPR pair. So number of VSEPR pair is 4. So if the number of VSEPR pair is 4, what is the electron pair geometry? What is the electron pair geometry? This is tetrahedron, right? That is tetrahedron. That is tetrahedron. Now you see there is no lone pair. So if there is no lone pair, the electron pair geometry should be the molecular geometry, should be the shape of the molecule. So therefore, shape should be tetrahedron. Shape should be also tetrahedron. But if there is any lone pair, for example, let me take this ammonia. In this ammonia, if they ask the electron pair geometry of nitrogen, you see 1, 2, 3, 4. There are 4 VSEPR pair. What is the electron pair geometry? That is tetrahedron. And if they ask the shape of the molecule, that is not tetrahedron, that is pyramidal. You should omit this lone pair. So, what is the shape will be? Shape will be pyramidal. Now it will be like this shape. In 3D it will be. Therefore, the shape will be pyramidal. If there is no lone pair, then the electron pair geometry is the shape of the molecule. Therefore, this is false, right? This is false. They have said the shape is trigonal bipyramid. It's wrong. Now, Roman number 5. All 3D atomic orbital of an atom are represented by quantum number NLM1. Principal quantum number, spin quantum number, azimuthal quantum number, and this one, N, L1, M1, S. Now here they have said the principal energy level is 3. So if there are in third principal energy level, how many sub energy level will be there? There will be 3 sub energy level. So how do we name them? 0, 1, 2. Okay, now this is the principal energy level, this is a sub energy level. After that, what will be the next level? The next level will be the what is the name? 0, -1, 0, +1 to this orbitals. -2, -1, 0, +1, +2. Here in third principal energy level, how many subshells will be there? There will be 3 subshells. This is S subshell, this is P subshell, this is D subshell. In S subshell, how many orbitals will be there? 1 orbital. How do I name that orbital? That is 0. Likewise, in P subshell, how many orbitals will be there? 3 orbitals. How do I name them? -1, 0, +1. In D subshell, how many orbitals will be there? 5 D orbitals will be there. -2, -1, 0, +1, +2. That's how I name them. So in the question, what they have said, all 3D atomic orbital of an atom are represented by 3, 2, 1. It's wrong. No? You see what they have said. They have said all 3D atomic orbital. Now, what are the 3D atomic orbitals? How can I name all the 3D atomic orbitals? It should be like this, right? 3, 2, -2. Let me erase this. 3, 2, -2. And then, how do I name them? 3, 2, -1. After that, 3, 2, 0. 3, 2, +1. 3, 2, +1. 3, 2, +2. Then only I can say I have named all the 3D atomic orbitals. But here 3, 2, 1. 3, 2, 1. Here they have said only 1 atomic orbitals are represented by this, not all 5 atomic orbitals. Therefore, it's wrong. There are 5 atomic orbitals for 3D. For third energy level, T subshell, there are 5 atomic orbitals. So here they have given only 1 atomic orbital, not all the 5 atomic orbitals are not mentioned here. Therefore, that statement is wrong. False. Roman number 6. Addition of an electron to a gaseous phosphorus atom is an exothermic process, whereas for gaseous nitrogen atom, it is an endothermic process. Now we'll see. What is this actually? This is electron gain enthalpy. Electron gain enthalpy. The energy released when an electron is added is the exothermic reaction, and the energy that we should supply to add an electron to an atom, that is an endothermic level. If we supply energy, that is an endothermic process. If by the addition of electron, if the atom releases energy, that is an exothermic process. Now there is a graph, right? There is a graph to remember. This is the graph. Here, this is the variation of energy level. This is 0, upward is plus, down is minus. For second group and for 8th group and the 5th group, in 5th group, the first element is the endothermic process. Now let me draw the graph for you. Now this is the second group, this is for 8th group, and this is for 5th group. This is something for first group, and this is for first group. First, second is marked, third, fourth, fifth is marked, sixth, seventh is like this. Here, second group. If I add an electron to second group element, then I should supply energy. I should supply energy. This is the graph which I had drawn for first electron gain enthalpy. To add an electron to an atom, how the variation of energy will be, whether I should supply energy or else by the addition of electron, the energy is released by the atom. If I add an electron to second group, then I should supply energy, that is an endothermic process. For eighth group also, if I add an electron, then the energy should be supplied by myself to add the electron to that atom. Likewise, in fifth group, only nitrogen, only the first element in the group is endothermic process, but for other elements in the group, that is an exothermic process, which means by the addition of electron, energy will be released by the atom. We no need to supply energy, that is exothermic. And for all other groups, it is an exothermic process. The addition of an electron to gaseous phosphorus atom is an exothermic process. Phosphorus will be somewhere here. Therefore, addition of electron to phosphorus atom is an exothermic process, while addition of electron to nitrogen atom is an endothermic process. Therefore, this is a true statement. That's it. Statement questions are clearly explained. If you have any doubt, you asked in the comment section, I will reply to you. Now we'll go to the B part. Draw the most acceptable value structure for the molecule SF3N. Now you know the electronegativity variation: fluorine, oxygen, chlorine, nitrogen, bromine, iodine, sulfur. It goes like this. So here what are the molecules given? SFN. Nitrogen is somewhere here, fluorine is here. So sulfur should be obviously beyond this nitrogen. Therefore, sulfur is the least electronegative among this SFN. So sulfur should be the central atom. Okay, sulfur should be the central atom. SF3N. Now we'll consider the total number of valence electrons. 7 plus 7 plus 7, that is 21, plus 5. For sulfur it's 6. So 21 plus 6 plus 1 is 7. 7 plus 5 is 12. 2, 3. 3 no. 32. 32 total number of valence electrons. Now we should subtract the electrons in the bond pair. 1, 2, 3, 4, 5, 6, 7, 8. From 32, if I minus 8, from 32 if I minus 10, 24 no. 24. This is 24 is the total number of valence electron. Now how many pair of valence electron? 24 by 2, that is 12 pairs. 12 pairs of valence electron. Now let me distribute this 12 pairs to the terminal atom first. Then if any other electrons are remaining, let me distribute to the central atom. 12 pairs now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now we have distributed all the 12 pairs to the terminal atom. Now we should see whether the octet is completed. You see whether the octet is completed. For valence electron, the electrons in the terminal atom, octet is completed. You see the central atom. Octet is completed now. For sulfur also, octet is completed. Now octet is completed. Now we see the formal charge. How the formal charge will be. For fluorine, there should be 7 valence electron. It has 7 valence electrons around itself. No charge. Here also no charge. Here also no charge. For nitrogen, there should be 5 valence electron. But here how many valence electrons are there? There are 7. 1, 2, 3, 4, 5, 6, 7. Therefore minus 2 charge. For sulfur, there should be 6. But it has only 4 valence electron plus 2. Now something interesting. You see, sulfur belong to third period. Sulfur belong to third period. If any elements, sulfur belong to third period, what is the speciality in third period when comparing to the first and second period? In third period, the elements will be having d orbitals. The elements will be having d orbitals. Therefore, it has many vacant orbitals. No, they will undergo promotion, and they can form bonds. More than 4 bonds can be formed by this sulfur. Because it has d orbital, they can form more than 4 bonds. They can form more than 4 bonds, and the maximum number of bonds is 6 bonds. You must have studied this part in theory. I wanted to give a detailed explanation. Sulfur belongs to the third period, therefore it can form more than 4 number of bonds, more than 4 bonds. That is, it can form maximum number of 6 bonds can be formed. So it is actually, what is the type of bond? Dative bond. Yeah, dative bond is going to form here. Dative bond is going to form here. Dative bond is a type of covalent bond. So here you see here, if there are two opposite charges and it has only four bond pairs are there, only it has 4 number of bond pairs, it can form further 2 bonds can be formed. Additionally, it can form 2 bonds here, and also it has charge separation. +2 -2 charge separation is there. To separate these charges, there should be certain energy between them. Our charges will try to attract each other. To separate them and keep it there should be certain energy inside them. What do you mean by it has certain energy? If it has high energy, then the stability will be low. It will be less stable. Stability will be low. Therefore, in the question they have said to draw the most acceptable Lewis structure. It means the stable structure. Here, what I can form? I can form a dative bond here. I can make this lone pair as bond pair. So if I do like that, what will happen? Bond will be formed. Now you see the charge distribution. Here there should be 6, but it has 5 valence electron. Therefore, +1 charge. Here -1 charge. There should be 5, but it has 6 valence electron. But you see here, sulfur can form 6 bonds now. Surround them, it has 5 bonds. Now it has formed 5 bonds. Additionally, it can form another 1 more bond. Therefore, here they can form another 1 more bond. Here, this lone pair will become the bond pair. If the lone pair will become the bond pair, it will form another 1 more bond. Now we'll see the charge distribution. There is no charge distribution. 1, 2, 3, 4, 5. There should be 5. It has 5. No charge. There should be 6. It has 6. Therefore, no charge. You see, there is no charge separation. This is the most acceptable Lewis structure. Yeah, most acceptable Lewis structure. This is the answer. Okay. Now we'll see the B Roman number 1 is done. Now Roman number 2. Roman number 2. They have given a structure and they have told us to draw another 2 Lewis structure for this molecule. They have given the resonance structure and they have told us to draw another 2 Lewis structure or resonance structure for this molecule. Here, oxygen, double bond carbon, double bond carbon, double bond carbon, double bond oxygen. Here 2 lone pairs, 2 lone pairs. Okay, how to draw the resonance structure? Making bond pair, bond pair. By shifting those two, we can work we can draw the resonance structures. Here, what I can do? I can make this lone pair as the bond pair and this bond pair as the lone pair. So here is the structure. Now to separate the resonance structures, we should show this type of a symbol. No? Now when you are writing in the writing book, you will write the resonance structures in this format. No, in this order only you will write. So you should put the symbol like this. But as I do not have any space there, I am writing it below. So I have put the arrow like this. So how the structure will be? Now we will see the charge distribution. Here plus charge, here minus charge. Now what else I can do? Yeah, I can make this lone pair as the bond pair and this bond pair as the lone pair. Correct, right? And then I can draw another structure also. Here I can make this lone pair as the bond pair and this bond pair as the lone pair. Correct, right? What else I can draw? Yeah, they have told us to draw 2, but here I had drawn 3. You can draw further resonance structures also. You can think and do it, right? So they didn't ask the stable or unstable structures. They have said just to draw resonance structure. It can be stable or unstable. You say whether this structure is a stable or unstable structure. It's unstable structure. Why it's unstable structure? You see, oxygen is highest electronegative oxygen. Oxygen is highest electronegative element. So if the highest electronegative oxygen has positive charge, is it a stable structure? No, it's an unstable structure. If this contain negative charge, then it is stable. Because the electronegative oxygen atom contain positive charge, it is unstable. And what's the other reason is the less electronegative carbon containing negative charge is unstable. Okay, and this is also unstable structure. Yeah, this is somewhat stable, and yeah, this is unstable structure. This is stable structure. Here, no charge distribution. Yeah, no charge distribution. This is a stable structure. So yeah. Roman number 2 is done. Not 3. Roman number 2. Roman number 2 done. Now we are going to Roman number 3. Roman number 3. Based on the Lewis structure given below, state the following regarding the carbon, nitrogen and phosphorus atoms given in the table below. Let me draw the structure. Fluorine, carbon double bond with oxygen, nitrogen, lone pair carbon, phosphorus, chlorine, chlorine, chlorine. Okay, this is the structure. And This is how they have named them. 1, 2, 3, 4. 2, 3, 4. VSEPR pair. VSEPR pair, electron pair geometry, shape and hybridization. Hybridization. C1 into C3P4. C1 into C3P4. Okay. VSEPR pair around the carbon. 1, 2, 3. Electron pair geometry, that is trigonal planar. Trigonal planar. Shape trigonal planar, because there is no lone pair. Trigonal planar. Hybridization 1, 2, 3. sp2. N2. What is the VSEPR pair? 1, 2, 3. 3. What is the electron pair geometry? That is also trigonal planar. Trigonal planar. But you see there is a lone pair, so what will be the shape? Shape will be something like this. This is angular. This is angular. Angular. And what is the hybridization? 1, 2, 3. It has 3 VSEPR pair, therefore sp2. VSEPR pair C3. 1, 2. 2 sigma bond. What is this one? Linear, right? Linear. Electron pair geometry is linear. Shape is also linear. Shape is also linear. What is the hybridization? sp. It has 2 VSEPR pair. P4. What is the VSEPR pair? 1, 2, 3, 4. It has 4 sigma bond. 4. What is that? And this one? Electron pair geometry. That is tetrahedron. Tetrahedron. And what is the shape? That is also tetrahedron, because there is no lone pair. And what is the hybridization? It has 4, therefore sp3. Therefore sp3. Is it? Okay. I'm going to clean this. Roman number 4. Identify the atomic or hybrid orbital involved in the formation of following sigma bond in the Lewis structure given in part 3 above. Numbering of atoms is as in part 3. 1, 2, 3, 4 and 5. 4, 5. Roman number 1, between F and C1. So, sorry. Okay. 1, 2, 3, 4. Between F1 and C1. Between F and C1. You can take this as the sigma. Now there are only sigma bond is formed. They are asking atomic or hybrid orbital involving in the formation. Now this is the terminal atom. Now you can, for this terminal atom, you can take as the hybrid orbital as the example, or else atomic orbital. Hybrid orbital or atomic orbital. Now it's azan. Please wait for 2 minutes. Sorry, you can forward the video and check it. Now fluorine, for there was the terminal atom. No? For terminal atom, you can write as hybrid orbital, or you can write as atomic orbital. So the answer can be now, what is the hybrid orbital of fluorine? What is the hybridization of fluorine? 1, 2, 3, 4. No, 4 means sp3. No, you can write as sp3 hybrid orbital, or else how can you write? Now fluorine belong to second period, no, so it's 2p. Valence now the electron involving in this bond, fluorine and carbon bond, 2p atomic orbital. For terminal atom you can put this hybrid orbital or atomic orbital. Now carbon, for carbon what you should put, what is the hybridization? 1, 2, 3. No, therefore sp2 hybrid orbital, fluorine and carbon. Next one, carbon and nitrogen, sp2 hybrid orbital, sp2 hybrid orbital, and for nitrogen 1 2 3 sp2 hybrid orbital. Next one, for n2 and c3 sp2 hybrid orbital and 1 2 2 no 2 VSEPR pair, therefore sp hybrid orbital. Now for Roman number 5, p4 and cl. p4, this is for Roman number 4, c3 and p4, c3 and p4, right? p4 is this one. What is the hybridization? 1 2 3 4. 4 means sp3 hybrid orbital, sp3 hybrid orbital. Roman number Roman number 2 is between carbon and nitrogen, that is sp for carbon 1 2 3 sp2 hybrid orbital, and nitrogen also sp2 hybrid orbital 1 2 3. Next one, this and this sp2 hybrid orbital and sp hybrid orbital. Next one, this and this sp hybrid orbital and 1 2 3 4 sp3 hybrid orbital. Next one, this and this sp3 hybrid orbital. And for chlorine you can put the hybrid orbital, or else you can put atomic orbital. What is the hybridization? 1 2 3 4, 3 lone pairs and 1 sigma bond, that is sp3 hybrid orbital or 2p atomic orbital. 2p or 3p, right? 3p atomic orbital. Okay, now that's it. And also the Roman number 5, I'm going to clean this. Roman number 5, identify the atomic orbital involved in formation of pi bond, n2 and c3, n2 and c3. Now between n2 and c3, you see the pi bonds are formed between only their atomic orbital. The hybrid orbital are not involving in formation of pi bonds. Hybrid orbital are involving in formation of only sigma bond, not pi bond. N2 and C3, what is the atomic orbitals involved? 2p atomic orbital of nitrogen and 2p atomic orbital of carbon. And between carbon and phosphorus, the 2p atomic orbital of carbon and 3p atomic orbital of phosphorus atomic orbital. Now Roman number, not the Roman number, part C. Part C, Roman number 1, variation of first ionization energy. Now for this type of question, it's easy to draw the graph and check it. 1 2 3, it goes right. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Boron, carbon, nitrogen, oxygen, fluorine, neon. Variation of first ionization energy. You see what they have asked? They have asked for sodium. Now you know what happens to first ionization down the group. What happens to first ionization energy? When the down the group, what happened? First ionization energy decreases, because down the group size increases. When size increases, first ionization energy decreases. So you know, if lithium is something above, and lithium is above than sodium, no. Now when we see the first group, sodium is below lithium. Because sodium is below the lithium, the first ionization of sodium should be lesser than lithium. Therefore, sodium should be somewhere here. If I do graph for second ionization energy, Down the group, the ionization energy decreases now. Therefore, sodium should be less than lithium. Then, boron. Boron is somewhere here. Next, phosphorus. Phosphorus should be somewhere here. Because phosphorus is below the nitrogen. No? Down the group, ionization energy decreases. Phosphorus is less than nitrogen. Then, beryllium and nitrogen. Beryllium, nitrogen. So what's the variation? First is nitrogen, next is phosphorus, next is beryllium, next boron, next sodium. This is the variation. Nitrogen, phosphorus, beryllium, boron, sodium. Okay. If there is a first ionization energy variation, draw this graph and check it. That's easy to get the answer. Now Roman number 2. Electronegativity of nitrogen for NH3 is NH3, NOCl and NO2Cl. NOCl. You know the Lewis structure now? I'm just drawing the Lewis structure. NOCl, no formal charge here for NOCl. Next one, NO2Cl, NO2Cl, NO2Cl. A minus charge, a plus charge. Next one, the NH4 plus and CF3NC. NH4 plus now. NH4 plus and CF3NC. 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 Plus charge, minus charge. There is a certain order that you have to check to find which atom is highest electronegative. First is hybridization. First is hybridization. How do you check with hybridization? First is hybridization, next is charge, next is oxidation number, next is terminal atom. The nature of the terminal atom. If the hybridization same, check the charge. If charge same, check the oxidation number. If oxidation number is same, check the terminal atoms involving in the bonds formed with the central atom. How do you check this hybridization? If the S character increases, then the electronegativity increases. Now if you take this SP, SP2 and SP3, what is the S character? 1s and 1p, 50% S character. For SP2, it will be around 33%, 33.33%. For this one, it will be like 24%. So you see the percentage of S character is highest for this one. So when percentage of S character increases, then the electronegativity increases. When charge increases, electronegativity increases. When oxidation number increases, electronegativity increases. Terminal atom, when we come to the example, we will check it. Okay. So you see here, now if we see the hybridization of all these atoms, here this is 1, 2, 3, 4, sp3 hybridization, 1, 2, 3, sp2 hybridization, 1 2 3 sp2 hybridization, 1 2 3 4 sp3 hybridization, this one sp hybridization. From this, what's the conclusion that you can get? This should be the first one. This should be the number one, because you see this is sp, sp2, sp2, sp3, sp3. So the sp has the highest percentage S character, therefore sp should be the, so the CH3NC should be the nitrogen in CH3NC should be highest electronegative. Now this is over now. Now with hybridization, game is done. Now with charge. Now we'll see the charge. And what should be the second one? Either this or this, no, because when comparing this sp2 and sp3, the percentage of S character is 33.33%, here 25%. So the percentage S character of sp2 is higher, therefore the nitrogen with sp2 hybridization has the highest electronegativity. So among this and this, now the second one should be either this or this, and the third one should be either this or this. Now from second one we have to choose, no, which is second place and the third place. Yeah, how are you going to choose this? From these two, charge is same, no? Now we will see the hybridization is same. Now we will see the charge. What is the charge here? Plus charge. Here what is the charge? Zero charge. Therefore it is obvious this is the second one, this is the third one. The third one. So from this charge also game is done with these two. Now for this is with these two, hybridization same. We'll see the charge. You see it has a +1 charge. This is a 0 charge. Because this has a plus charge, this should be the 4th position. This should be the 5th position. Okay. CF3NC, NO2Cl, NOCl, NH4 plus, ammonia. That should be the order. Okay. Roman number 2 done. Then what is this Roman number 3? Roman number 3, quantum number of electrons in an atom is given. The energy of electron, how the variation of energy of electron will be. When the electron is further away from the nucleus, that electron should be the electron with the highest energy. The energy of electron will be maximum when it is the furthest distance from the nucleus. Therefore, if you check the order, you see 310 minus half, 310 minus half, next one 300 plus half, 300 plus half, 200 plus half, 200 plus half, next one 2 1 plus 1 half, 2 1 plus 1 half, next one 3 2 minus 1 half, 3 2 minus 1 plus half. Now you see the Aufbau principle. You know the Aufbau principle, right? First one 1s2, 2s2, 2p6, 3s, 3p, 4s, 3d. This is the electrons are distributed with increasing energy level. So you see here, if I check this one, third energy level, third principal energy level, second subshell. So there are 3 3 3 and 3. You see this is this plus half electron is distributed in 3 means 0 1 2 d, right? Here 3 n l ml ms. This is the principal energy level, this is the sub energy level, this is the orbitals, this is the spin quantum number, that is plus half or minus half, that you know to check here. Here you see at which position this electron is distributed, at which orbitals it is distributed in 3D atomic orbital, because it is S subshell, P subshell, D subshell. In 3D, this electron is deposited. This electron is deposited in this orbital. You know, the first energy level, second energy level, third energy level. Third energy level is further away from this nucleus, so that the electrons in the third energy level should has the highest energy. So with this and this, which has the highest energy level? This one, right? Because this is in 3D orbital. 3D orbital. If I check this one, this is 3D. If I check this one, in the third principal energy level, it is in S subshell 0, 1, 2. It is in S subshell 3S subshell. If I check this one, this is 3P subshell 3P subshell. Okay, therefore 3D should be further away from the nucleus. Therefore the electron at this 3D atomic orbital should has the highest energy. This should be the first one. This should be the second one. This is because 3P subshell. This is third one. From this and this, you check here. I will see here. Wait. Second principal energy level. There will be 2 subshell, 0, -1, 0, +1. This is S subshell, P subshell. In this P subshell, there will be 3 orbitals. You see here, what is the quantum number given here? 2, 0, 2, 0, 0 plus 2, 0, 0, sorry. So what does this mean? The electron is distributed in the S subshell. 2s. This is in 2s subshell. What is this? 2, 1. This is 2p subshell. So S is further away, P is further away from the nucleus. P is further away from the nucleus. Therefore, the electron at this atomic orbital should has the highest energy. First one, second one, third one. This is fourth one. This is fifth one. That should be the order. Now, let me take this as A, B, C, D, and E. The E should be first one. E should have the first energy level, the highest energy. Next one is A. Next one is B. Next one is D. Next one is B. Next one is C, right? C. This is the order. So that's it. If you understand this, give something good in the comments. Okay, when it is clear, put a thumbs up in the comments. And if you have any doubt, you can ask in the comment section. I can reply to you. I'll reply to you. And then please share this with your friends. And please like, share, and subscribe to Brainy Elements. And also click the bell icon. That's it for this video. Thank you.